Alright, so here is the ladder of powers that I was talking about. So these, they call it the ladder of powers because, like I said, every transformation can pretty much be brought back to a power, whether you're rewriting it as root or the reciprocal or an actual power. So the highest power, although I did show a cubed example, but for the most part, you're going to use this as like a step ladder. You're going to, the power of 1 represents your actual data. So if when you graph it, it's linear, you're not going to change, okay? So this is where you start. Notice that you don't really go higher up on the ladder. If a square is getting closer to straight, but it's not perfect, then you might try cubed. Or like when we did the cubed, and I talked about how weight of a fish is kind of like volume. So sometimes those cubed ideas are more intuitive. So the square root of the data values, you want to use this when your data is unimodal and skewed to the left. So if you graph it, and you can look at a histogram to begin with rather than a scatter plot. But if you notice that you have some skewness to the left, you want to try squaring things. Like I said, 1 represents the raw data. The 1/2 power is the square root. So this is when you have counted data. 0 would be not really the 0 power, since 0 power doesn't do anything. This is really the logarithm. So, or natural log. So if a square root doesn't work, you might try a logarithm. Oops, I just realized that my word log is off to the side. I'll zoom out a little. So the biggest thing with logarithms, because if you think back to pre-calc, if you had me for pre-calc last year, the domain of logarithms, we can't go into the negatives. So if we have measurements that cannot be negative, this is a really great place to start. Anything that grows by percentages, such as salaries, populations, logs often tend to be a good transformation. And when you're in doubt, start there. If your data has zeros, you might want to try adding a small constant, although I'm going to show an example in a minute that has a 0 and the logarithm works. And I'm not going to add a constant. So logs, probably the best place to start, because in a minute I'm going to talk about different ways you can do logarithms, and so it might be the best place to start, and then either go back up the ladder or down. Negative 1/2 power is the negative reciprocal square root. This one doesn't come up, so I mean, even in the description, it's uncommon, but it might come up. Honestly, I'm not going to throw that one on the test. That to me is just evil. And then the negative reciprocal. So ratios of two quantities, miles per hour. The reciprocal is often a good choice. You have about a 50-50 chance that the original ratio was taken in the wrong order for simple statistical analysis. And so taking the reciprocal would often make it linear. And then often the reciprocal will have simple units, hours per mile. So change the sign if you want to preserve the direction of the relationship. If your data has zeros, you will have to add a constant because we can't divide by 0. So the next thing that I want to talk about before we get into an actual set of data. So if the original data is linear, then you don't need to do anything to transform. I don't know why I have a pencil, excuse me. Nothing. If you're working with data that looks logarithmic, which by the way, I guess I'll do this in pencil. So logarithms, they look something like that. That's not perfect, but you get the idea. That's what the shape is. So what you want to do to transform the data is you want to take the log of x. So you'll end up with a plus b times log of x. If it's exponential, I should have put more space in between these, I apologize. Exponential, that could be like that. It could go this way, that's exponential decay. What you want to do there is take the log of y, which is what we looked at yesterday. And then a power model, you're going to want to take the log of both y and x. In statistics, this is often called the Goldilocks transformation because it fixes a lot of things. So I suppose you could start there if you want. The only thing there is then it becomes really complicated to use predictions. I like to only mess with one, but if you're having really stubborn data, logging both. And when I say log, you can also use natural log interchangeably if you prefer the natural log. But when you start to log both things, making predictions and that kind of stuff become a little more complicated. So I like to mess with only one variable. So now we're going to look at our example. So a student opened a bag of M&Ms, dumped them out, and ate all the ones with the M on top. So he took a bag of M&Ms, dropped them, and just let them fall, and only ate the ones that landed with the M showing up. If they didn't have the M, he didn't eat them. He put them back into the bag and repeated the process. So after the first dumping, when he finished, he put the remaining 30 M&Ms back in the bag, repeated the process over and over until all the M&Ms were gone. So below, there's a table and the scatter plot showing the number of M&Ms remaining at the end of each course, like a 6-course meal. So we have the courses, M&Ms remaining, our scatter plot. So what transformation would you think of trying first to make the data linear? Why? Try it. I don't know why I put a question mark there. Try it. We'll make that an exclamation. And the biggest thing, remember, you need to look at the residual plot for your transformation to see if it's truly linear, not just the scatter plot. Because sometimes the scatter plot can look linear, but when you find the residuals, it's not. So, if we look at the original data, we have almost that exponential decay idea. So for an exponential, we want to take the log of y. So the y's are the M&Ms remaining. So let's see. Since the scatter plot looks exponential, and I'm just hopefully zoom out, exponential, and it is decay because he's eating them, right? Let's try. We're going to log y. So we're going to leave x alone. So I said what transformation I'm going to try first, the reason why, and now we're going to try it. So I'm going to switch to Google Sheets. So we have the course, M&Ms remaining. I can't spell. So there are 7 courses, so he did this 7 times before all the M&Ms were gone. So we're going to log the number of M&Ms. Now yesterday we did log, so this time I'm going to do natural log just so that you see an example of that. So we're going to natural log M&Ms. So just like before, we're going to highlight that column, go up to the formula bar, we're going to put equals. You're going to go over to your function. Remember, yours should just be at the far right. Mine is in a separate menu because I'm zoomed in. Go to math, and then go to the L's, ln, natural log. And we want to do it on the y's, so the M&Ms remaining. So that's B2 to B8. Hit enter. Pull it down. Now, on this one, well, it even tells you function natural log parameter 1 value is 0, should be greater than 0. You can't take the natural log of 0. Natural logs have to be greater than any number greater than 0, but not equal to. So when I graph, I'm going to leave course 7 off. So that's on the ladder of powers. It said you might want to add a small constant. I suppose if you really wanted to, you could add 1 to them. I'm rethinking my thought process right now. You know what? Let's just leave it like this. So all I'm going to do when I graph the course versus the natural log of M&Ms is I'm not going to put course 7 on there because it's in error. So we're going to highlight course only through 6. And then the natural log of M&Ms all the way down. We're going to insert our chart. Scatter chart. Hey, it actually gave me the right one. So notice that my data looks very linear. And so we're going to get our trend line. Because remember, scatter plots can look linear, but your residual chart is what tells you whether a linear model is a good fit or not. So get our trend line. Which remember, go to Customize Series, scroll down, click Trend Line, scroll down, click Label, use Equation. And then we're going to make our residual plot. So our equation is the natural log of y, or M&Ms, is equal to negative 0.681 times x plus 4.06. So here, we're going to do predicted M&Ms remaining. I cannot spell. So highlight. Sorry. And we are going to highlight all the way down because our X that we put in is 7. So we are going to put 7 in there. Well, yeah, let's put 7 in. So that equals negative 0.681 times our X's, which are A2 to A8, and then plus 4.06. Enter. There's our first predicted, and there's the rest of our predicted. Now, when we do the residuals, remember we're looking, our least squared regression line was for the natural log of M&Ms, so we're going to do the natural log of M&Ms minus the predicted M&Ms. And here, if you tried to do C8 minus D8, it's not going to like you, so I'm only going to do the first 6 courses. So this is equal to my natural log of M&Ms, so C2 to C7 minus D2 to D7. Enter, and then we're going to fill in. So there are our residuals. So then we're going to do the course. And again, I'm only going through 6. And my residuals, we're going to look at our chart. We want to scatter. And we don't have a pattern, which is a good thing. So we chose a good model. Now, if I went through that and I didn't find a good model, that's where the ladder of powers comes into play. So if the natural log didn't work, I would maybe think about taking the square root or going down the other way and doing the negative reciprocal square root. I'd probably, just for the sake of making my life easier, try the square root first because that one seems a lot harder. Plus, it is an uncommon transformation. So then the last thing, we have to use our model. Oh, I should have written this down. We had natural log of M&Ms was equal to, what was it? That one. Negative 0.681x plus 4.06. So then, to make our prediction for the original number of M&Ms in the bag, so that would be course 0 before we dumped any out. So we're going to put 0 in for x. So natural log M&Ms is equal to negative 0.681. We're putting 0 in for x plus 4.06. So that times 0 goes away, and then when we add 4.06, we just get 4.06. Now, yesterday we talked about how we can take something that's in logarithmic form and convert it to exponential form. The same holds true for natural logs. Natural logs, for those of you that aren't familiar, are in base e, so it converts to e to the x equals y. So when I rearrange this, I'm going to get e to the 4.06 equals m&ms, because the natural log is gone away. Predicted m&ms, excuse me. On this calculator, so the natural log button, so e, if I hit second natural log, that gives me e. Then I type in 4.06, and we get 57.97. Now we're talking about m&ms, so I'm going to round up, and we're going to say that he probably had around 58 M&Ms to begin with before he started dumping them out and eating only the M's. Your homework, if I can remember where I put it, is really just one problem. You are going to make the scatter plot for some data on parts for mammals. Make the scatter plot, describe what you see, use transformations to linearize the relationship. So what transformation did you use and why? Get your least squared regression line, and then make a prediction.